Hey everybody, it's Mr. Carr again. Today we're going to be looking at 8.1 day 2. We're going to continue our vector work, talking about a couple different types of problems here. So we're using vectors to solve a navigation problem. So an airplane is flying with an airspeed of 475 miles per hour on a heading of 0 to 70 degrees. So remember from before that is starting from true north and it's going to go 70 degrees. So it's going to go something kind of like this. I'm going to go, let's go with blue to start it. So we're going to go like this about here. This is going to be my 70 degrees. Okay. And that is traveling at 475 miles per hour. Okay. If an 80 mile per hour wind is blowing from a true heading of 120 degrees, determine the velocity and direction of the plane relative to the ground. So the 120 degrees, if I kind of look at it this way, if I can look at just the, whoops. Okay, if I want to look at maybe just right here, for example, okay, 120 degrees is going to blow from this area here, from my 120 degrees bearing. Okay, so let me model that. I'm going to do that in red. So from this point here, okay, we have a wind that's coming from basically over here. Okay, so this is my 120 degrees heading. Now, what that happens is because it's coming from that direction, the path of the wind is actually blowing this way. Okay, so if this is my 120 degrees, I'm going to make it into this kind of idea here. That looks like it's close enough. That's going to be my 80 miles per hour going that way. So the idea in this scenario is the resultant vector is the actual path of the airplane. So the resultant vector is going to be from here to here. Okay, so we notice that we're making a triangle there. So in order to model that triangle, I'm going to do a couple of things here. So first thing is, notice with the 70 degrees here, that's going to make, let's see here, green here. That's going to make this 20 degrees to make that up to 90. So then if I want this measurement here, oh, sorry, hold on one second here. Oh, thing I forgot about this part too. If I look over here, this is going to be 30 degrees because if it's at 120 like this, if it travels 120 here, I'm basically traveling 90 and then plus 30. So that's got to be a vertical angle to this one. So this one's also going to be 30 here. Okay. So let me start drawing that triangle just to make it a little bit clear for myself. So we're starting from point A. That's where the airplane is starting from here. We're going to have this side length here. That's going to be 80. This one's going to be, whoops, not this one. This length here is going to be 475. Okay. This length here, if I get, one second here. Let me see here. So if I look at, what am I missing here? Oh, yeah. So if I look at the fact that this is 70 degrees here and this is 20, this 20 degrees is going to match up to here because of the parallel lines idea. So I can label this one as 20 as well, meaning my angle right here, which is this one, is going to be 30 plus 20 to give me 50. A lot going on with this one. So we got 50 degrees there. All right. So I have enough to do for now. So let me go ahead and start by solving this. I want to find this x value, which is going to be the total, that's going to be the total miles per hour that the plane is traveling based on the two vectors coming together. So I'm going to do law of cosines here because I do law of cosines because I have side angle side here, side angle side with the angle being included. So law of cosine states that x squared is equal to, it'll be 80 squared plus 475 squared minus 2 times 80 times 475 times the cosine of 50. Okay, so then I'm going to take the square root of both sides here, and I plug this all in my calculator at once, so I get x is equal to 427.987. Okay, for the next part, what we need to do is we need to find this angle here. I marked it earlier, but I need to find that angle. In order to do that, I'm going to have to know what this angle is. So I can do now my law of sine. So this is angle A. I'm going to do the sine of A divided by 80 is equal to the sine of 50 divided by 427.987. Okay, so from here, we can just we multiply both sides by 80. So the sine of A is equal to 80 times the sine of 50 divided by 427.987. And then to solve for my actual angle A, I'm going to do my inverse sine. So I'll do inverse sine of 80 times the sine of 50 over 427.987. So I'm going to plug this in my calculator just like this, and I'm going to use my calculated version here, not a rounded off version. So when I do that, I get 8.23 degrees. So 8.23 degrees is this little section right here. So that means I could find my last angle that I want right here, which is going to be 90 degrees minus, what was it, minus 20 minus my 8.23. Because 8.23 and 20 is that right there, so this is going to be the rest of it. So when I subtract those away, I get 61.77 degrees. So what this means, I'm going to round to my nearest tenth in both cases. The resultant vector, which is this one right here, we're starting from a true heading, so that means it's going to go clockwise here. It's going to be that 61.777 or 61.8 degrees. So the airplane is going to be traveling at this right here. So it's going to be 428 miles per hour at a bearing of 061.8 degrees. Okay. Again, I'm taking this value here as basically my magnitude, and my direction is from here. Okay. There's a lot going on with those, but it's just, they can get tricky. You just got to make sure you kind of break them down step by step and look at them as their pieces. All right, while digging in his garden, Will pushes a shovel into the ground with a force of 630 newtons and an angle of 70 degrees with the ground. Draw a diagram that shows the resolution of the force that Will exerts into its rectangular components. So the idea here is that we're basically creating a triangle here. So since Will is going on an angle of 630 newtons, there is going to be a vertical component and a horizontal component to how he's doing. He's not going straight down, he's going on an angle. Okay, so with our horizontal push, that's going to be my X, and my vertical push is going to be a Y. So we see that we create a triangle here, and more specifically, a right triangle. So we're going to use trigonometry to help us find those different components. Okay, so if I look at this, if this is my 70 degrees here, I can label my hypotenuse, my opposite, my adjacent. I'm going to set up trig twice. So for the vertical part and for the horizontal part. So vertically, we're going to deal with opposite and hypotenuse. That's going to be sine. Now, as a shortcut, since its sine of 70 is this y over 630. So sine of 70 is equal to y over 630. So that means I multiply both sides by 630 here. So 630 times the sine of 70 is going to equal to my y component. I plug that in my calculator just like that, and I get 529.0 newtons. Let me write that a little better. Newtons for my vertical force. For my horizontal is going to be based on adjacent and hypotenuse, so that's going to be cosine. So that means the cosine of 70 is equal to x over 630. Multiply both sides by 630. So I get 630 times the cosine of 70 is equal to just x now. So I plug this in my calculator just like that. So when I do that, I get a value of 215.5 newtons of force. Okay, so again, the idea here is even though Will is pushing this direction with the 630, that force on an angle is being made up of a vertical down and an X to the left here in this case. Okay, so it's made up of two components, like vertically and horizontally versus just on that angle. Okay, and that is it for today. Just want to talk about a couple more vector type of problems that we can see with these, especially with word problems. But that is it for 8.1 day 2. All right, take care, everybody.